The entire star, a white dwarf, goes unstable, collapses, and becomes a supernova. Get ready for a cosmic event unlike any other. Like any star, it will run out of fuel in its core and start changing. It begins to bloat and get so large that it will engulf the orbits of Mercury and Venus, coming very close to Earth. Scientists are predicting that a terrifying supernova explosion will soon light up our skies, visible from Earth with the naked eye. It's very unstable, and it's about to explode now. It could happen tomorrow. This rare and awe-inspiring phenomenon could outshine entire galaxies and offer a glimpse into the raw power of the universe. Imagine looking on the horizon and seeing the sunrise cover half the sky. That would be terrifying. To understand the significance of this event, we first need to grasp what a supernova actually is. In simple terms, a supernova is the explosive death of a star. It happens when a star reaches the end of its life cycle and can no longer sustain nuclear fusion in its core. This leads to a catastrophic collapse followed by a powerful explosion that releases an enormous amount of energy and light. These explosions are so bright that they can briefly outshine entire galaxies, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. What makes this upcoming supernova particularly terrifying is its proximity to Earth and the potential effects it could have on our planet. The star in question is known as Betelgeuse, one of the brightest stars in our night sky, located in the constellation Orion. Betelgeuse is a red supergiant, an aging star that has expanded to nearly 1,000 times the size of our Sun. For years, astronomers have been monitoring Betelgeuse closely, noting its unusual dimming patterns and erratic behavior. These signs suggest that Betelgeuse could be nearing the end of its life, and when it finally goes supernova, it will be a sight like no other. The explosion will be visible even during the day, and at night it will rival the brightness of the full moon. But while the spectacle may be breathtaking, it also comes with potential dangers. A supernova is a tremendous interstellar explosion that occurs when the universe's largest stars explode, while smaller stars simply fizzle out. The death of an astronomical heavyweight is a showstopper. It has spent its life cannibalizing its own materials, and sometimes those of a neighboring star, for fuel. When there is nothing left for it to consume, it collapses in on itself and then explodes outward in a death knell that outshines other huge stars and sometimes entire galaxies for days, weeks, or even months. In a galaxy the size of our Milky Way, a supernova explosion should occur about every 50 years according to statistical calculations. The most recent supernova in the Milky Way was thought to have happened in the late 1600s. According to experts, up until 2006, a group of interstellar particles that had eluded detection for 23 years turned out to be the afterglow of a supernova that had occurred only 140 years before. The flare-up went unnoticed by astronomers due to cosmic dust, which also obscures the vast majority of the estimated 1 billion supernovae that explode outside our galaxy annually. On the other hand, a pair of binoculars can reveal some supernovae due to their extreme brightness. A supernova that burst 21 million years ago may be seen by Northern Hemisphere Earthlings in September 2011 when they peered into the Pinwheel Galaxy. This galaxy is visible from above the Big Dipper handle but is obscured to most southerners on nights without clouds. A star chart makes identifying constellations a breeze. After all, humans have been tracking the locations of these stars and planets for a very long time. But what if a guest star unexpectedly shows up among its well-documented counterparts? It's likely the remnants of a supernova that burst into existence eons or millennia ago, and the light from that star is only now visible to our eyes. It doesn't take a professional degree to make an astronomical discovery. In January 2011, a 10-year-old girl found a supernova in a galaxy 240 million light-years away. When new, brighter, and more distinct pinpoints emerge in the sky, scientists frequently turn to amateur astronomers to keep an eye out for them. As their temperatures rise, stars on the verge of a supernova transition from red to blue, and the Doppler effect keeps supernovae somewhat blue. The light from their explosions is traveling toward Earth at such a high velocity that it appears blue to the human eye. Also, a supernova won't budge from its spot like a comet or a commercial airliner. Astronomers living in ancient China made the first record of a supernova some 2,000 years ago. The point of light seemed to be a brand new one to them, and they couldn't make sense of it. but the object vanished without a trace after 8 months of documenting the new star. Despite the fact that this elusive star may have faded into obscurity, a renaissance of interest in the finding occurred in 2006 when astronomers noticed similarities with supernova remnants recorded in ancient China. It was a light bulb moment. Similar supernovae have been discovered in galaxies around the universe, including our own Milky Way. A supernova that was visible to the naked eye was found in 1987, close enough to Earth that telescopes weren't necessary to see it. The Milky Way galaxy's neighbor, the Large Magellanic Cloud, is where this supernova went off. When scientists found its debris burning brighter in 2011, it made history once again, this time as it entered a new decline stage. The supernova remnant's brightness became more pronounced as the remnant's residual mass expanded and collided with a debris ring released before the explosion. The X-rays and heat released by the collision made the remnant appear brighter. Where did this star's self-destruction start? From its humble beginnings as a baby star formed when gas and dust buckle under the strong force of gravity, a big star emerges. The core of a young star draws in more gas and dust from the interstellar medium as it heats up. This maturation process can last as long as 50 million years, after which there is a lustrous adult stage that lasts for another 10 billion years. Where does all that dazzling light come from? Nuclear fusion of hydrogen into helium, a somewhat denser and heavier element, is the process that powers stars. Stars undergo fusion in their centers, and the resulting energy radiates outward, illuminating the universe and keeping the dense core from expanding. The end of a star's life begins when its hydrogen fuel can no longer be used to create helium. The core's temperature increases when it starts to collapse due to less energy radiating outward. The star's expansion is caused by hydrogen fusion, which only takes place in its outer layers. It becomes a red giant. A red giant will lose its outer layers to become a white dwarf. A star of sufficient mass will eventually burst into a supernova, consuming those layers and combining them into heavier and heavier elements. If the star's gravity is insufficient, it will instead expel its outer layers into space, which cools them. The collapse of its core will cause an explosion beyond anything we've ever seen on Earth unless we bundle and simultaneously explode a few octillion nuclear bombs. Does anyone know how far away Betelgeuse is? Since it is the closest possible supernova, although precise distances cannot be determined, it is likely to be close to 1,000 light-years, which is relatively close by galactic standards. The eventual supernova explosion of Betelgeuse is a fact that will be known to us, however, its timing remains uncertain. Very little is known about the past of supernova observations in our Milky Way. Seeing a galactic explosion, particularly one as nearby as Betelgeuse in our lifetimes, would be an incredible feat. Internal thermonuclear fusion reactions are what give stars their luminosity. The process is rather straightforward. They use energy to build more complicated elements by fusing simpler ones like hydrogen into helium. Large stars will eventually run out of simple fuels but will continue to burn more complicated fuels until their cores are iron, at which point nuclear burning will stop. After fusion stops, the extreme pressures and temperatures inside a star decrease, and the star itself becomes much more massive. After collapsing, the star rebounds in a spectacular explosion known as a supernova. Once their fuel supply is depleted, large stars like Betelgeuse undergo a Type II supernova explosion, characterized by rapid collapse and explosive expansion. Whatever is happening inside a star, its remaining fuel. The proximity of Betelgeuse to collapse determines when it will explode, but how is Betelgeuse functioning internally? Betelgeuse is believed to be in the final stages of core carbon burning, according to recent findings. For a big star like Betelgeuse, the carbon burning period lasts about 1,000 years. If we are indeed near the end of that stage, then Betelgeuse is likely about to burst, maybe even in tens of years. But aren't other options also possible? Without a doubt, there are, since surface conditions seldom alter in the late stage, close to carbon exhaustion and beyond. The researchers argue that it is not possible to pinpoint the exact evolutionary stage. What goes on deep inside a star tells the story, even if astronomers can only see the surface. What the paper's authors mean is that Betelgeuse explosion could happen sooner than expected based on observations, data, and models. Importantly, though, they have no idea where the star is in its main carbon burning process. According to a few of the data-fitting models, carbon burning could continue for quite some time. Betelgeuse could potentially burst tomorrow. Is that why Betelgeuse dimmed? The sudden and noticeable dimming of Betelgeuse in late 2019 caused excitement all around the globe. This phenomenon is now known as the Great Dimming of Betelgeuse among astronomers. Many people thought and hoped that the great event, the explosion of this relatively close star, was about to happen. While it was happening, Betelgeuse has not yet exploded, even though it has faded, brightened, dimmed again, darkened again, and so on. According to astronomers who studied data from multiple observatories, including NASA's Hubble Space Telescope, the brilliant red supergiant star Betelgeuse blew its top in 2019. A large portion of Betelgeuse's apparent surface was obscured as the star released a massive surface mass ejection. Nothing like this has ever been observed in the behavior of a typical star. Coronal mass ejections are regular occurrences when our Sun regularly expels portions of its delicate outer atmosphere, the corona. However, compared to regular coronal mass ejections, the Betelgeuse surface mass ejection released 400 billion times more mass. Consequently, it appears that the star's 2019 great dimming of Betelgeuse was caused by a cloud of hot gas that momentarily obscured part of the star's light. Clearly, some game is afoot at Betelgeuse. Is it happening again? Even if Betelgeuse were to explode, it would be too far away to cause any damage, let alone wipe out life on Earth. According to research, in order for a supernova to cause harm, we would need to be within 160 light-years of it. The distance to Betelgeuse is probably 4 times as great. The night sky will be graced with an incredibly breathtaking sight, a star that is incredibly bright for everyone on Earth when Betelgeuse ultimately explodes. The proximity of an exploding Betelgeuse will also please expert astronomers. In the aftermath of the supernova, they will have a star to study. On the other hand, the explosion will be entertaining for both professional and amateur astronomers. However, Betelgeuse will be greatly missed by those who love to see it as the brilliant red star in Orion. Meanwhile, a dead star will soon spark a once-in-a-lifetime display in Earth's skies. The astronomical wonder Corona Borealis, an arc-shaped constellation, was visible to the abbot of Urg Abbey in modern-day southern Germany in October 127. He wrote in Latin that it was originally a faint star that shone with great light for a time and then returned to its original faintness. Neither did he be the first nor the last to see it. This stellar apparition emerges then vanishes every 80 years or so, and that's because it isn't really a star at all. That abbot witnessed a thermonuclear explosion 3,000 light-years away. It came from a white dwarf, a stellar zombie that's devouring matter from a nearby red giant star. Once a century, it gets full, and when it does, it erupts, unleashing a week-long hellfire. This is T Corona Borealis, often shortened to TCB, and it's what astronomers call a nova. A word that is derived from the Latin description of these events as new stars, which many pre-modern observers assumed them to be. TCB last erupted in 1946, and its behavior suggests that its next paroxysm is due any moment between now and September. At that point, TCB will be a transient diamond in the stellar crown of its constellation, visible to the naked eye. Astronomers will not view this latest burst as a random event but rather as an opportunity to gain a better understanding of novae, the often overlooked culprits behind cosmic mayhem. Novae are completely weird events, says Bradley Schaefer, an astronomer at Louisiana State University. However, TCB is unlike any other. Contrary to expectations, it goes through a wild ride of increasing and decreasing brightness. If you want to know anything about a population, researching its outliers might be the way to go. When TCB goes off, a large fraction of every telescope in the world is going to be pointed at it. It is helpful to have a basic understanding of novae in order to grasp the excitement that TCB has generated among astronomers. In each nova, a white dwarf, the tiny remnant of a dying star, and a normal companion star, in this instance a bloated red giant, are thrown into a deadly combination. The hydrogen from the companion star falls to the white dwarf's surface as a result of the dwarf's gravitational pull. Since the white dwarf is so dense, an unstoppable chain reaction leading up to a nuclear explosion is set off when this veneer becomes hot and eventually ignites. This is like a gigantic hydrogen bomb that blasts off the entire atmosphere of this Earth-size white dwarf, not to be confused with supernovae, which are more catastrophic explosions that lead to the destruction of a star. However, that in no way diminishes their significance or awe-inspiring nature. In a series of devastating eruptions, novae manage to preserve their stellar parents while enhancing their heavenly environments with a powerful blend of newly formed elements. One of the primary sources of lithium may be novae, which also produce oxygen, nitrogen, and carbon, three of the most essential ingredients for life. So deciphering novae is essential to comprehending the pathway from astronomy to biology. If astronomers are fortunate, recurrent novae, those that explode at least once every 100 years, can serve as reliable study guides. Even with TCB, they've only discovered approximately 10 in the Milky Way thus far. The eruptions of this system have only been recorded for 1217, 1787, 1866, and 1946. This is despite the fact that TCB appears to be quite reliable, but ancient astronomers have shown it to be unpredictable. After careful analysis of its previous two recorded eruptions, experts have determined that it is expected to go off in around 3 months, give or take, and will be visible for a few days. Several of the world's most prestigious observatories are already planning to seize the opportunity to capture the explosion of TCB in optical, radio, X-ray, and other light wavelengths when the time comes. Also involved are amateur astronomers, with such all-encompassing monitoring. TCB could go from being a cosmic anomaly to providing solutions to mysteries that affect all novae. For example, how hasty are their outbursts? X-ray astronomy can help with that. When an eruption happens, you have this hot glowing fireball, says Kick, one that emits X-rays as it expands. The white dwarf's expelled shell cools down and subsequently emits optical radiation. The time difference between the X-ray and optical flashes can clock how fast the jettisoned material is moving. Almost massless neutrinos are produced by several types of cosmic cataclysms and can show secret data about the powerful processes that released them. However, neutrino detection is infamously difficult, and no neutrino has been detected from a nova to this point. It would be helpful, though, to know when and where a neutrino-making nova is expected to flare up. A fresh perspective on the explosive physics of all novae could be revealed if it turns out that current-generation neutrino detectors are able to detect TCB. Although many astronomers are interested in nova explosions, the question of what they could evolve into is perhaps more intriguing. A pair of stars, including at least one gas-guzzling white dwarf. In this type of supernova, much like in regular novae, the stars undergo mass exchange. However, their thermonuclear explosion is so powerful that it destroys the matter accreting on the white dwarf. A common scenario for a Type Ia supernova is a white dwarf that has consumed an enormous amount of star matter, reaching the Chandrasekhar limit and becoming 1.4 times heavier than the Sun. When the white dwarf's mass gets too great for it to sustain, a thermonuclear chain reaction sets up and it explodes into its own destruction. Consequently, the most important thing to know is how these white dwarfs manage to accumulate enough matter to surpass the Chandrasekhar limit. Since Type Ia supernovae should theoretically explode in the same way no matter where they are in the cosmos, their explosions are useful yardsticks for measuring enormous distances between galaxies. Therefore, if astronomers can find any anomalies in the comparable but smaller explosions of regular non-supernovae, it could slightly alter their Type Ia-based measurements of the cosmos. Every time a white dwarf explodes, it may not completely devour or eject all of the matter it has accumulated. Therefore, scientists are interested in studying how regular novae work, how much of that matter stays on the white dwarf and how much is blown off in a nova. This apocalyptic balance sheet can be checked during TCB's next outburst. The white dwarf is mainly made of carbon and oxygen, while the red giant is donating hydrogen, providing a bulk ingredients list from which relative proportions within a nova's ejecta can be ascertained. As a result of TCB's impending explosion, astronomers hope to gain insight into the three perplexing peculiarities of this particular nova. We are unaware of any additional novae that display these characteristics. The majority of novae remain faint and only become very brilliant during eruptions, but TCB is unusual in two respects. Firstly, it is in a condition of modest brightness for around 10 years before and after an explosion, during which it emits a hot blue violent light. What causes the high state to deactivate? Why does the high state activate anyway? We don't have the faintest idea as to what's going on. The second strange feature is its pre-eruption brightness dip, which happens about a year before the eruption. It heralds an impending eruption and is also a strange and unprecedented enigma. According to some theories, the white dwarf's accreted matter acquires a dusty covering that hides the blazing bonfire below as it nears its well-known phase. It is possible that the pre-eruption dip is caused by TCB ejecting gas before its eruption, which then forms dust shells and shuts off light from the central system. Lastly, it appears that TCB has a secondary eruption a few months following its explosion. This eruption is bright, but it doesn't quite match the brightness of the first outburst. It may continue for a few weeks or months. A long-lasting mystery has been the secondary maximum. According to Munari, unfortunately, he does provide a potential remedy in a recent preprint. It's all a delusion, not just another eruption. The white dwarf flaring the red giant's observable hemisphere during its accretionary phase and outburst. While the white dwarf may be cooling down after the eruption, the red giant side facing the inferno is still very hot. When this hot side turns to face Earth, astronomers mistakenly see this glow and think it's a second eruption. When TCB actually unleashes its hellfire, everyone will be able to assess Munari's idea. What would transpire if the stars disappeared is another important issue to ponder. Our ability to establish the calendar, navigate, and advance scientific knowledge from agriculture to physics would be severely hindered in the absence of stars. Changes in global power dynamics, human migratory patterns, political landscapes, and commerce routes could result from a world without stars. Astronomical navigation, culture, trade, and the emergence of new world powers would all undergo dramatic changes in a starless sky. Ultimately, the sun is a star. Imagine a world devoid of stars, the sun, and life. If you happened upon this cosmos devoid of stars and life, you could find yourself wishing you had brought a warmer coat as you floated through a freezing expanse of emptiness. Decent burritos would be harder to find. Every once in a while, a neutrino would blip into or out of existence. Then how about we reframe it? What if the stars were invisible in this hypothetical universe? Earth still has planets and a sun, but we can't see any stars outside our solar system. We can assume this is due to the fact that a dark nebula encircles our solar system. Nebulae are massive clouds of gas and dust, typically merging to create stars. They shine brightly because of this, but every once in a while, a large cloud of interstellar dust will obscure their light. Because of its low temperature, our solar system is located inside a dark nebula, but we got a bad galactic hand when our sun formed. That's what we'll pretend for the time being. As life emerged on nebula Earth, the stars dimmed and the solar system dipped into a dust cloud. The night sky became increasingly black on the night that the first courageous little lungfish wriggled onto land. As the dust piled denser over the subsequent several million years, the night sky was filled with mere remnants of the last most brilliant stars that had broken through the nebula, a handful of red splotches in the darkness. All that humanity could see when they finally looked upward were the planets and the moon. On nebula Earth, humans lacked the necessary technology. Using the stars has been an integral part of human history, allowing humans to establish calendars, navigate, determine when to plant crops, and advance scientific knowledge, particularly in the field of physics. An important source of power for Egyptian priests was the ability to foretell the path of the stars. It is more difficult for the priests on nebula Earth to recruit helpers for the pyramids when they don't have a divine mandate. However, with so many technological constraints, it would be challenging to foresee the far-reaching consequences. Therefore, let us zero in on one specific area: navigation by the stars. Keeping an eye on the shoreline allows early European sailing around nebula Earth to circumnavigate the Mediterranean Sea. A sundial and compass make it easy to find your bearings during the day, but at night, you'll need the stars to pinpoint your exact location. Sailing becomes more perilous when you can't see land. Even a little storm might make it impossible to tell where you are. Any maritime journey longer than a day has an ever-increasing margin of error due to the increasingly erroneous bearing, making travel over open seas practically unfeasible. All major human migrations on nebula Earth take place on land, since the planet lacks advanced navigators, even though they have been inhabited since land migrations occurred. When sea levels were low, the Americas, Greenland, and Australia continued to be geographically separated.